Hi, everyone. Welcome to today's WiDS Datathon Winners Panel discussion. I am Valerie Elliott, the WiDS Datathon Program Director on the WiDS Worldwide team, and I'm also here with our Datathon collaborators from Anna S. Bauer's Women's Brain Health Initiative, Child Mind Institute, and Kaggle. So I love you each to give a little intro about yourself. Maybe we'll start with Ariana from Child Mind Institute.
Hi, everyone. I'm Mariana Zonazzi, and I work at the Child Mind Institute, which is an independent nonprofit that is focused on transforming the lives of children and their families, children who experience mental health and learning challenges. And also, we provided the data sets for this challenge. So I'm very excited to hear about solutions and approaches. My role as CMI involves leading open science initiatives, driving data sharing efforts, as well as fostering collaborations and research partnerships. And yeah, so I'm really excited to meeting all of you and hearing about your approaches.
And let's go to Amy next.
Great, thank you, Valerie. So my name is Amy Kuzieski. I'm a professor at Weill Cornell Medicine in the radiology department and Cornell University in the computational biology department. And I've spent my life trying to study the brain using neuroimaging. And recently, with Nina, we became the co-directors of the AI core for the Anna S. Bauer's Women's Brain Health Initiative. It's a new initiative that's focused on studying everything that happens in female bodies, looking at menstrual cycles, menopause, pregnancy, all these things that have been classically understudied in the literature. And I'm so excited to be hearing about some of the talks today and telling us about the things that you did to analyze the data. So hopefully, I'm sure I'll learn something new from you all. So thanks.
Great. And Nina, would you like to go next?
Yeah. Hi, everyone. I'm Nina. I'm an assistant professor at UC Santa Barbara, and I work in machine learning and AI methods to study brain images. And together with Amy, I'm co-director of the AI core for the Anne L. Bowers Women's Brain Health Initiative. Also super excited to see what you have done with this challenge.
Great. And Maggie.
Hey, this is Maggie from Kaggle, and we have been supporting the Datathon for many years, really for for your benefit. We have seen what the Datathon has done to really improve the lives of people who participate in terms of introducing you to data science, building new collaborations with people sometimes across the world that you'd never imagined that you'd work with. So we are super excited to continue to support the WiDS Datathon.
Excellent. Well, let's get started. So this year in our Datathon 2026 challenge, all of you analyzed fMRI data in order to diagnose adolescent ADHD. And it was a fantastic challenge. We're really glad that you're all here to learn from our winners. Today, we have a pleasure of hearing from each of the winning teams. They will each share their solutions. They'll take about 10 minutes to walk us through what they did, any insights they had, and then we'll have a short Q&A with them as they finish their presentations. If you have any questions for the winners, please feel free to put them in the chat. The rest of their teammates will also be engaging in the chat to help answer your questions. And last but not least, just to make sure we avoid any disruptions for our winners, please keep yourself muted for the duration of the call, and we'll use the chat, put anything in the chat that you have comments on. All right, so let's get started with our first place team. So first up, we have first place team Jenna from Hanoi, Vietnam, and Tu Nguyen will be presenting on behalf of the team. So over to you two. Here, you'll need to take yourself off mute first.
Hello, I'm Thu Nguyễn. I'm from Zena team. I'm Thu Nguyễn. I'm a senior student at FPT University, majoring in information assurance. Recently working on a large language model for cyber threat intelligence education, and I had experience with data processing before this competition, but this was my first time working with medical data. I only started learning about it around the last 2 weeks of the competition. The next is my teammate, Mạnh Nguyễn. He is also a senior student at FPT University. Majoring is computer science, working on a large language model for cyber threat intelligence application. He has experience with machine learning model and has um, e- um, he worked with tabular data. His knowledge helped us a lot this competition, and today I'm excited to share our solution that won first place at the Women in Data Science Datathon. Um, in the summary, training methods are sample, XGBoost, and LGBM model with hyperparameter optimizer. We have most important feature is MRI track as and scan and SDQ externalizing percent, SDQ emotional problem percent, and 5TS row and 91 column. The tool use Pantas, Sklearn, XGB, LGBN, and Optioner. Training time is about 32 minutes on Kangaroo CPU. Next slide. In the feature selection, engineering part, for missing value, we use iterative imputer with Lasso CV. Cross validation is S to fill missing data. After several trials, we found the generating too many derivative features on this small dataset results in overfitting. So we only retain about the 15 feature that were strongly agree great from the social demographic column. With the stamp-based processing only, we normalize the SDQ and ABQ column to 0 to 1 with min-max scale, then to some column for their two groups. After calculating the percent for each column, I score on column in the group, calculating the graph balance, occupation and education to create two column edu different and OCC different. We also remove some columns such as enroll year and study site, scan location. Their decisions were based on our experience, where the column did not have much significance for prediction. Next slide. Regarding the most important feature in the ADHD model, we have a hyperactivity scale, generating impact score, educational graph, along with some percentile column of FDQ and ABQ. Next slide. In the In the SecF model, we have 58 row and 91 column, which are the connection between the dorsal prefrontal cortex and the orbital frontal cortex, along with the new SDQ column like SDQ internalizing percent, emotional problem percent, and hyperactivity percent. Next slide. With the training methods, we use separate model for its objective. For ADHD outcome, we exclude fMRI feature because if their include did not improve CV and significantly slow down training. For SecF, we include fMRI data. which capture sex-specific brain connectivity pattern. We use 4-type model including LGPM regressor, LGPM classifier, XCP regressor, and XCP classifier. We also tried Casboard, but removed it due to the competition running out of time. Next slide. Cross-validation and pooling strategy. We use a custom S4CV strategy based on parent the ADHD outcome column. Each time, the number of ADHD and non-ADHD cases were divided equally. About the model, in total, we trained 26 model with the 7 model with full S4CV and 19 additional model training on the full data using pseudo label from the S4 model. Regarding the way to for the female ADHD, we did not use them due to bias to work class one in the sex app prediction and on hyperparameter optimization was performed using Optimal. Next slide. About the threshold optimization generate in the one-fold model, we use pseudo label for the test data. Basically, the objective is initialized by calculating the average of the F1 score of the training data and the pseudo label of the test data. Then from the distance of the threshold for the best score to 0.5. We expect the new model to have the same results when applied based on the output of the old model, but will have the threshold close to 0.5. This helps us have new threshold. ADHD threshold from 0.86 to 0.8 and 6F threshold from 0.06 to 0.15. Next slide. Important finding we have the first using the regression model with binary objective. The symbol of the feature is over enduring when data is limited. If we use BCA speed up testing, but reduce CV in our experiment. Opportunity for hyperparameter tuning and use beta kit regression-based model for ADHD prediction. Next slide. With simple model path, we were able to keep around 94 to 97% of the best performance by reducing the number of stack model. You can see table using only one LGPM regressor one-fold model for 6F prediction can achieve F1 around 0.8 and one LGPM regressor one-fold model achieve 0.79 and one XCP regressor model is 0.77. If not using hyperparameter, then can achieve 0.8 with only 4 types of stack model. If combining CPA with 100 components can achieve 0.79. Training time will be improved much better if trained up a little bit on accuracy when it's only takes about 90 seconds or 30 minutes in our test. This is all part of our solution. Are you have any question?
Thank you so much. Great presentation. Do we have any questions for Tu? Ariana, Amy, or Nina, if you have any questions for
Actually, a question. Well, great presentation, first of all. I was really interested in the approach that you had in defining as feature the education difference and the occupation difference between the parents. So I was just curious about how you got to this idea because it played out well, and I saw that it was a relevant feature in the model in the end.
Tu, is that something you can address?
When we create the when we create the feature is what basically trial and enroll. Initially, we create and trial many other feature like splitting behavior, cutter using KNN and or UMAP. We also try creating some feature through neural network model. If they improve the overall CV by about 0.03 to 0.08, then they will keep over. Otherwise, they were discussed. We found that create more variable from the top feature uh, create more breakthrough. For example, the SDQ and ABQ column group, they were both column belonging to the most important feature. We found they had uneven scale, so we did not normalization and basically doing the min-max scale for each column and then calculating sum and percentage based on the work group. They actually turn out to the uh, out to be better alternative to the original column. About the two columns of the gap between education and work. Okay, this word actually in the top 10 of the ADHD model. I'm not too I'm not sure about this. We think they're going to different in parenting. Basically, the bigger the graph, the more likely they are going to be very different parenting style. I mean that different can lead to psychological problem in children or um, teenager, and then I think that's all.
Thank you.
Thank you. Excellent job. Well, thank you so much, and congratulations again on your efforts. Wonderful. All right, we will go on to the next team now. So next we have the second place, Team 11 from Cambridge, Massachusetts in the United States. And Beiju Yao will present on behalf of the team. So I'll hand it over to you, Beiju.
Can you hear me well?
Perfect. Thank you.
Okay, good. I'm teamed with Xiaoyue Zhang, who's busy moving and couldn't make it. We were co-workers in the current company that I'm at, and she was looking for a different job because she's been at this job for like 4 years, and she wants a new opportunity. So we decided to study together and participate in this competition together.
Mm.
And my background is in image analysis, and she is biostatistics, so more towards the real world evidence side of the data. So, and I think will be a good combination because she will handle the metadata and I will handle the MRI data. And then next slide, please. Yeah, I already covered this. The one thing I want to highlight is that the novel approach used here is the autoencoder to denoise the functional MRI data. When I was exploring it, I tried like traditional methods, and then it reached a bottleneck of especially in the gender prediction. The metadata doesn't help much, and most of the signal come from the functional MRI data. So I used the autoencoder to embed the thousands of dimensions into like 16 to 64 dimensions, depending on the model. And then I added a supervised part to the autoencoder, meaning that the autoencoder has 2 tasks. One is to reproduce regenerate the input data. The second task is to predict gender or ADHD diagnosis. So that constraint. So I was playing between the balance between these 2 tasks and tuning how much does each task contribute to the loss function. And then doing this parameter tuning allowed the model to perform better in the gender prediction, but not in ADHD prediction, just using the functional MRI data. Next, please. Next, please. Because both autoencoder and the gradient boosting trees have built-in feature selection automatic feature selection method, so I didn't do any manual feature selection. And Xiaoyue used a robust scalar on the metadata, and then to integrate the functional MRI embedded space and the metadata, we just concatenate these features together for the final prediction. Next, please. Next, please. The other thing we noticed is the entire training data is very unbalanced. So we did a subsampling of the data with auto replacement, and that can generate as many sets of subsamples from the training data as we want to. And then we train each autoencoder model, and there's a mistake in the typing. We train one autoencoder model and one gradient boosting model, and compare for both of the target predictions, which one performs better, and that model is selected for the submission prediction. And next, please. Next, please. So I mentioned this already. Autoencoder model is better at predicting gender, and the gradient boosting model is better at predicting ADHD outcome. And we used 50 sampling iterations, meaning that each subsample, each subsample contains a different subset of the data to train the models. And the model, when I look at the variance of the outcome, it's pretty big. And that just shows how much biological variance is it in the data. And then we also noticed that some individuals have consistent predictions, but others don't. I think if we had more time, we would evaluate what makes some individuals have large variance from a model to model, and whether we can see any correlation from in between that and the metadata. Next, please. Next, please. Yeah, the simple model is a logistic regression. It's not doing very well. Next, please. Next, please. Oh, yeah, this is my overall summary. The data is very noisy, and we have AWS from work, so we were able to access GPU and train the model as much as we want, and did several iterations of different methods. And also tried a graphical neural network that couldn't compete with autoencoder, so we just didn't use it in the end. And the fun part is the exploration part of trying different methods and learning how it performs with these kinds of very noisy data, and seeing that gradient boosting is very good, even though it's a simple approach. Next, please. Yeah, I'm fast. Any questions?
Wonderful job. Thank you. What questions do we have for Beiju?
I have one question. First of all, congratulations. That was very clear, and congratulations on your second place. You said you use graphical neural networks. Do you mean graph neural networks? And if so, which ones did you try? And yeah, can you give a bit more details on
I
that?
tried the most basic convolutional and then use the features like first transform the it into the adjacency matrix, and then create the issue is the weighted edge is really hard to deal with, and I tried in labeling them with like binning the from like there's not many methods that have positive and negative binned weights, and what I did was binning the like close to 0 and in the middle, and far from 0, close to 1 on.
Yeah.
And like there's like 5 different bins, and encode them as 5 different kinds of edges.
Interesting. And what did you put on the nodes?
The nodes are like there's a node to it's called node to VEC. It's
Got it. Yeah.
node to VEC.
Not, okay.
Yeah, that's the simple way. I also did all zeros in the node. It doesn't propagate. So
Yeah.
yeah.
And how bad was it? Do you remember? Do you remember how bad it was? You said, yeah.
Let me think. I don't remember
Yeah.
because I didn't do it at a large scale. I only selected like in the beginning part. I was exploring the autoencoder bits that model that a graphic neural network that I built every single time. So I just
Yeah.
decided,
Yeah. Makes sense. Thank you. Thank you.
thank you.
Awesome answer.
Wonderful. Well, thank you so much. Thank you, Beju, for a wonderful presentation.
Thank you.
All right, we'll go on to the next team. Next, we have the third place, Team ABCD from Santa Barbara, California. And Catherine Liu will present on behalf of the team.
So hi everyone, my name is Wei Yu, and you can call me Catherine as a preferred name. And together with my teammates Zhida Wang, we get the third places in this competition. So it's a great honor to be here to share our experience and approach to at this challenging yet rewarding competition. So next page. Next page. So to introduce ourselves, Zhida and I are mathematical students at the University of California, Santa Barbara in the US. And I'm currently a junior, and Zhida is a freshman year. So although that we are not experts in the data science part, our theoretical academic background provides us some fundamental knowledge in the deep learning models, and the practical experience from this competition significantly enhanced our skill and understanding on the deep learning models or data science field. And we believe that our openness to learning the new methods and models from others is kind of like advantage at this competition because we think that every model is worth a try. So we find a lot of methods and learn from them. So next page. So our strategy primarily involved using the ensemble methods and the GNN model. We identified the specific features that play the vital roles in the prediction. And for the ADHD, the important features including some SDQ questionnaire scores related to hyperactivity, conduct problems, some genetic impacts. So for the gender prediction, the brain image, the functional connectivity data is vital. So also to handle these missing data, we apply the multiple imputation by chain equations, the MICE method that we usually use in the data science. And additionally, we employ the optimal for hyperparameter tuning with the typical run duration between 10 to 20 minutes per iteration. That's in our computers, but we are not sure if others have better CPU, GPU to run. And the next page, please. So we think that the most significant learning was recognize the distinct values of the quantitative data in ADHD prediction compared to the important role function connectivity matrix in the gender prediction. Initially, we experiment with the categorical data using methods like one-hot encoding, but we found that they make little difference in the actual prediction. So we can conclude that the categorical data sets were generally less useful for this specific task. And next page. So going deeper to our feature selection process, we think that the data set to identify the most impactful variables. So variable important plot was essential tools in our flow to clearly visualize some feature impact. So we review this plot and we strategically prioritize some features and refine our models. So this can improve our performance. And this page shows the quantitative data repeatedly emerge as the critical for ADHD prediction. And we think it is likely due to their direct measurements of some relative behaviors and some symptoms. And next page, it shows that, next page, please. Oh, yeah, it is. It is the gender prediction heavily depends on the functional connectivity matrix, highlighting the biological difference captured by the brain image between the genders. So this insight prompts us to focus on the on some engineering meaning features on this matrix. And we did spend a lot of time on understanding this kind of new data and especially use them in our gender prediction. So the next page is about the GM models. We think that our significant innovation in our approach is to structure this GM model. By setting some correlation threshold to define the address, we represent the brain regions as not, and with address indicating some strong functional connectivity. And furthermore, each node was characterized by its degree, the number of connections it maintained, and it provides some valuable structural information. We think that it can generally greater enhance the effectiveness of our GNN models. And the next page. And next page, please. So our training method involved this diverse classification algorithm, including this model like logistic regression and USVC rich classifier, and this such classifier regression and SVC model. And this combination methods through the ensemble learning prove that it is effective, and particularly when we optimize with the optima to turn in the hyperparameter. However, we try to optimize the hyperparameter for each model individually, and it is less effective in our task. So the ensemble combination allows us the robust prediction and improve all the models generalization. And next page. Next page. So among our key findings, we think that the particularly striking discovery is that assigning double weight to female ADHD cases, this can significantly boost our prediction scores. On this observation, we think that it indicates some potential underrepresented or complexity related to the diagnosis ADHD in the females, and underscore the importance of some addressing gender bias in the medical dataset. And also, we think that experiments extensive with large models like various neural networks, some large language model. This did not yield some best performance. And so ultimately, we choose to refine ensemble methods to prove our effectiveness. And additionally, we think that the categorical data set provide limited utilization for both ADHD and gender predictions. It meets our initial expectations, so we did not use this kind of data set in our models. And this realization maybe guide us towards some better resource allocation during the model development, because we did not spend much time on this kind of data. And next page. So when we explore some simple models, we think that there's no quite actual simple models in our findings. But we think that the straightforward ensemble approach can get, with only quantitative data, can get a reliable ADHD prediction, and we use the also logistic regression as the third place as mentioned. It is not really great prediction, but I think it can give a hint that what kind of model we can use in the ADHD prediction. And I think for the gender prediction, there's no simple models can used, and we think that gender prediction is much harder than the ADHD prediction in our journey. So I think that this may caused by some biological complexity in the gender prediction. We are not sure about that. So that's this part. And the next page, please. Summarizing all the participant experience, initially we think that we should dedicate a significant time to the GM models, because we think that in the potential to use the brain connectivity image, and also use some graph theory for this gender prediction. But surprisingly, the ensemble methods outperform the GM models across all kinds of the brain image data, providing that ensemble methods were properly to manage can achieve the good results. And we think that it might caused by some noisy data in the fMRI image when they collect this data. We're not sure about that. Maybe if we can have we have large data set, we may achieve better scores if we use some neural network, some graph methods. And as a beginners in the data science competition, the collaboration learning environment provided by Kaggle is valuable because we can find lots of discussion there and we can learn a lot from them. They provide a lot of methods that are some ideas we can learn from. And also the regular weekly discussion between Jida and I sparkly some numerous ideas and improvements. And providing that teamwork may essential to our success. And discussion can make it easier to identify bugs, some errors, and gain valuable insights, such as the recognition of the reweighting female ADHD, the cases. And lastly, our motivation was from the curiosity about the brain image data. This is a novel and challenging data area that attract our interest and inspired by our dedicated participation. I think most people used to plot some similar graph. And oh, I'm sorry, I forgot to mention next page, but I am already in the next page. So we and still next page, please. Yeah, I think most people used to plot these similar things, the plots I present here to understand this unique data set. So we think exploring the connective matrix is to discover some new relationship and methodology when handling fMRI image was particularly interesting and rewarding. And this all. Thank you for your interest to our journey for this experience.
Excellent job. Thank you for a great presentation.
I actually have a quick question about the 2 times female, the weight.
The rating one.
So did it increase the accuracy of ADHD predictions in males as well, or was it just overweighting the females, which may be harder to detect and have smaller, more unbalancedness? Like there were more males with ADHD in the data set, right? So
Yeah.
was it just that it was improving the classification for females, or was it also improving the classification for the males with ADHD?
I think when we rated in the example one, we rated the ADHD, female ADHD directly, and we prove it actually improved a lot for the gender prediction, but ADHD improved, but the difference not much. As I think that with example one directly, we think that may caused by ADHD handling the mainly depends on the cognitive data instead of the the fMRI connectivity data. And when we use it in the gender prediction, we think that it improved a lot, much better than before, especially when we tried in the summation, when we submit our final prediction in the data in the website. And we think that may cause by when we reweight it and we insert all the data set into the example one. Because of the large data sets of the brain image data, it may improve a lot and the effect might be larger than when we predicting the ADHD. Because we think that the gender handling depends on the brain image data. And as the data set is quite a lot, so the difference might cause the larger than we expect. That's our thought.
Great. Well, congratulations.
Okay, thank you.
All right, we'll move on to the next team. And next we have 4th place, Team Data Raptors from Bangalore and Hyderabad in India. And Rohini Ramachandran will present on behalf of the team. So over to you, Rohini.
Yeah, hi all. So myself Rohini, and along with my team Raghuram, we actually participated on this WiDS Datathon. And yeah, first of all, we would like to thank the WiDS organizers and the Kaggle team for organizing this. So yeah, it was a challenging experience overall. And next slide, please. Yeah, to give a background about like myself, Rohini Ramachandran, I'm located in India, Bangalore office, and I have almost like past 6 to 7 years of experience in data science, and I'm currently employed with Wells Fargo as a data scientist. And my colleague Raghuram is located at Hyderabad, India location, and he has past kind of 9 years of experience in data science. Both of us are into Wells Fargo. So I'm from basically an electrical engineering background, and he has from electronics and communication background. So, and both of us have been trying for the past 4 consecutive years, and we have been participating in WiDS Datathon continuously. And this time we made up to the 4th position. Yeah, next slide, please. Yeah, so to give a summary overall, so the training methods that we used was an ensemble of light GBM, XGBoost, CatBoost, and logistic regression with voting classifier and threshold tuning. The most important features, in order to identify that, we used PCA compressed functional brain connectivity data, along with the socio-demographic and the metadata features, which included example like the parental education, strength, and difficulties questionnaire. So this was including the metadata and also the connectome data. The tools we used were Python, scikit-learn, LightGBM, XGBoost, CatBoost, PCA, Jupyter Notebook with VS Code, and we used GPU, specifically NVIDIA RTX 3090. And how long did it take? It was approximately 45 to 60 minutes for us with 5-fold cross-validation and an ensemble training on RTX 3090 GPU. So looking onto the leaderboard overall, so when we started this competition, we were on the public leaderboard with an F1 score of 0.77506. So we were on the 60th rank. And when it went onto the private leaderboard, our F1 score improved when it was on the unseen data set. It came up to around 0.814113, and we reached up to 4th level. Next slide, please. Yeah, talking about the feature selection. So in order to do the dimensionality reduction, so like when we looked onto the data set, the connectome features we could see was, it was huge. It was almost like 19,900 features it had. So given the high dimensionality, we used principal component analysis to reduce the feature size. And in terms of dynamic component selection, we kept like 90 to 95% of variance in each fold in order to avoid overfitting with the data. This approach helped us to reduce the noise, and it was as well as it improved the overall computation time while retaining the critical information. Next slide, please. Yeah, talking about the training methods. So here, then the input data, when we got it, when we looked on in depth, we did an data analysis. We understood like there were like 2 metadata files along with 1 connectome data. The metadata files altogether were like around 60 features spread across 2,213 records. But when we analyzed the connectome data, it was kind of huge data set with 19,900 features. So our first analysis was like, how can we retain the importance of each and every feature, and as well as we try to check on the curves of dimensionality. So that's where what we did was we actually merged or summed up all the metadata along with the connectome data. And after doing this kind of merging of all the data sets, we applied the principal component analysis. This was kind of a per-fold PCA. And on top of that, we applied the stratified k-fold cross-validation method. So on each data sets, on each k-fold applied PCA data, we had this ensemble models that are being run, like these CatBoost, XGBoost, LightGBM, and logistic regression. And every time the model was being trained on every fold of this data set, which was already kind of stratified, and it had a PCM applied on top of it. And then on these models, which were trained on this every fold, we had this voting classifier applied. So this voting classifier in turn actually took care of like giving a merge and then an average in terms of a soft voting system. And then on top of it, we had this threshold optimization. So the threshold tuning, we had basically taken care of in terms of checking that F1 score is being maintained. So when this threshold optimization was applied, we ensured like our F1 score was best in terms of giving the optimal probability cutoff. So not going by the default value of 0.5 probability. So every time, every set of k-fold was taken care, and then there was this threshold applied, and then the F1 score kept on improving. And then when it was run on the final predictions on the unseen validation data set, we got the best F1 score, which was able to diagnose the ADHD outcome, and as well as in terms of predicting was it female or not. So this was overall the pipeline that we had in terms of from the input data until the final prediction. Next slide, please. Yeah, talking about the ensemble models and the voting classifiers that we had used, we combined the strengths of multiple base learners, the gradient boosting models. But why did we choose this light GBM? Although, so going by the strength of each and every model, we know like light GBM is optimized for high dimensional data, and along with the GPU that we had, it helped us a lot. Similarly, XGBoost, it's known for its strong tree-based learning. And then CatBoost, it's great for categorical data. And at last, the logistic regression with a balanced class weight, we used it for baseline calibration. So we used all the strengths of each and every individual model. And when we assembled it together, along with the voting classifier, which takes an average of all the probability outputs and gives the average output probability for the better cutoff. So this became kind of the strength in terms of improving the F1 score. Next slide, please. Yeah, talking about what worked well. So as we were just trying out different PCAs. So when we started, we had kind of direct PC approach. Then after analyzing it further, we understood that the per-fold PCA actually reduced the overfitting and leakage. It took care of the data leakage part as well. And then threshold tuning. Yeah, it improved our F1 by finding the optimal decision boundary on each fold. So instead of losing the default 0.5 probability, so every fold of the data that was being trained on, it had its own kind of a threshold, which overall improved the F1 score. And then the multi-model ensemble technique. Yeah, we leveraged the strength of diverse models for a balanced approach. So this worked well for getting us the better score. And what did not work well, yeah, so like the per model weights in the ensemble. So like we had been participating in for the past few Kaggle competitions, like different data sets. And every time we found that when we had this kind of per model weight approach, like where you have suppose 3 or 4 different models, and you try to have a weight multiplied and then sum up in order to get the final output. Many times this ensemble having this kind of approach doesn't give you a better F1 score. So that's the reason this time we avoided that approach and we went with just having the kind of soft voting mechanism instead of not going by this per model weight. And similarly, no single model performed best across both the targets. And too few PCA components as well. Like then we started with around 70 to 80% of connectome data, and then slowly we improved it across, and that's how it helped us. And similarly, we understood like overtuning the hyperparameters also did not improve the cross-validation score as well. Yeah. So, yeah, next slide. Yeah, I think, yeah, that's all we had. So these are the discussion boards and our code repository. Yeah.
Thank you. Congratulations on a fantastic job.
Yeah, thank you.
Questions for Rohini?
I don't have a question. I just have a point of appreciation. It was a great presentation and great approach. I really want to appreciate this sort of bottom-up data-driven approach that you guys used. I think that is really interesting to see an approach where you consider all of the features, you try to find the best solution for both the targets, and in the slides that you had before, you conclude that this is not possible. It's not possible to have the best model for both targets. So I just wonder, maybe my question would be whether that's the approach you started to use from the beginning, or you selected this approach like as the best approach in the process.
Yeah, so I would say like we started first having all together. So even to start with, first we didn't even had this connectome data included. We first initially started only with the metadata, which was those categorical and quantitative data, which was altogether just 60 features. So it didn't give us better results. That's when we understood that these 19,900 features would give us even more better kind of a performance. Then the next level, we included the connectome data, which actually we then understood what kind of data it is. So when we analyzed it in detail, it looks more kind of a flattened matrix, which takes care of all the brain related features, how they are connected. So it is basically a 200 cross 200 matrix data, which came up to those huge 19,900 features. And then when we applied like directly on both the target variables, so though the F1 score starts looking good, but many times we have this problem of getting overfitting. So because there is this interaction bias that would happen, like the target one related whatever we are trying to predict would have an interaction bias with the target two variable output. So then when we had some kind of analysis, like how can this be avoided? That's where we had like having a two different kind of approach, like target one output being separated from target two output would give even more better results. So that's where these kind of, we had to create different functions which took care of kind of having this perfold kind of cross validations applied on two different targets on two different sets of training data every time, and then clubbing together at the end. It gave us a better performance separately in terms of ADHD and as well as the sex predictions of whether it is female or not.
Thank you. Fascinating.
Thank you.
Thank you very much.
Yeah, thank you all.
All right, we'll move to the next team. So next we have fifth place team, Fantasticians. Sorry, I have a hard time saying that word. From Bucharest, Romania, and Ioana Birlan will present on behalf of the team. So over to you, Ioana.
Hi, everyone. I would also like to start by thanking the organizers for hosting such an amazing edition. These themes always inspire us to participate since we do really treasure the novelty of working with such diverse data sets. Let me start by giving a bit of background about our team. So next slide, please. Next slide. Here we go. My teammates are Ana Maria Oprea, Bianca Consolencu, and Janina Petrașcu. We are a team of 4 girls who met 6 years ago when we began our bachelor's degree in statistics at the Bucharest University of Economic Studies. Since then, we've completed a master's in data science and applied statistics and have participated in several datathons. Most notably, last year we placed 3rd in the university edition, which was open only to students. This year, we're proud to have finally ranked among the top teams in the Global Datathon. It's been a long journey. We've actually participated in WiDS every single year since 2022. We are passionate about research, and all of us have published in academic journals. Currently, Anna is a business intelligence developer, Bianca is a data scientist, and Janina and I are PhD students and researchers at the Bucharest University of Economic Studies. Next slide, please. Our winning model was a voting ensemble of ICSIPU, slide GPM, and logistic regression. We decided to focus on generalization, calibration, and stability, and that is why we combine the strengths of tree-based models that are good for capturing interactions with the consistency of the logistic regression. To ensure that we weren't overlooking better alternatives, we experimented with a range of models such as the random forest, CAT-boost, ridge regression, and even graph neural networks. Ultimately, we found that the model complexity didn't always translate to better generalization. In terms of feature importance, the top predictors were behavioral assessment scores, and I will go into more detail in the next few slides. We also incorporated connectome-derived features from fMRI, though their impact was more nuanced, as we'll see later. The full training pipeline, including feature engineering and cross-validation, ran just under 2 hours. We didn't have access to GPUs, so we had to use our own laptop CPU. Next slide, please. Next slide. Now let's talk about how we prepared the data for modeling. One of the biggest challenges in this data set was the size of the functional connectomes. Each participant had nearly 20,000 features. We couldn't use these raw values directly, not just because of the computational cost, like I mentioned before, but also because we risked overfitting. So we applied PCA. We first handled the missing values in the connector matrix. We then ran a PCA and kept the top 50 components, which explained about 40% of the total variance. This step helped us reduce the 20,000 raw connectivity features into just 50 uncorrelated ones, essentially creating a condensed summary of the brain's connectivity patterns. This not only helped us in the model, but it also helped us run the model because it took a long time for us. We added these components to the dataset as regular features alongside behavioral and demographic variables. For models like XGBoost and LightGBM, this helped reduce the noise and correlations, and we had a better generalization. And finally, one of the most impactful parts of our pipeline was using a two-stage modeling approach. We first predicted the probability that a participant is female and then used that probability as an input to the ADHD model. I think that was what gave us such a good score in the end. This was based on clinical evidence. So ADHD can present differently in girls, often through more subtle internalizing symptoms. Using a probability instead of the binary sex label gave our model more context and helped it better capture these nuanced sex-related patterns in both the behavior and the brain connectivity. Next slide, please. This correlation analysis shows that ADHD is mostly strongly associated with hyperactive and externalizing behaviors, as well as the total level of behavioral difficulties, which are all consistent with what we read from clinical diagnostic criteria. We also see that children who show more pro-social behavior like empathy and helpfulness are less likely to be diagnosed, as are girls, reflecting well-known patterns of underdiagnosis in females where symptoms are often more subtle. These results reassured us that our model was learning from clinically meaningful patterns, which had basis from the medical literature. Next slide, please. We then looked at the features most correlated with sex. We see a clear behavioral distinction. Girls tend to score higher on prosocial behavior and internalizing symptoms like anxiety or sadness. Unfortunately, these are also patterns well documented in clinical psychology. In contrast, boys show elevated hyperactivity and externalizing behaviors, which helped explain the higher ADHD diagnosis rates among males. These differences gave our model a strong foundation for predicting sex, but they also helped make sure we didn't blur the line between sex traits and ADHD traits so that the model could remain accurate. I think it is worth pointing out that even smaller things like color vision or parenting scores showed subtle but consistent patterns by sex. I think this could hint at probably broader developmental or environmental influences, which perhaps in the future it is worth looking into. Next slide, please. We also use the Shapley additive explanations, or most commonly known SHAP values, to understand how the model actually made predictions, so not just the correlations. You can see that behavioral scores have the strongest positive impact on predicting ADHD, which aligns with our previous findings. However, interestingly, features like enrollment year also appear, suggesting possible cohort effects, something we couldn't catch from correlation alone. So this is why it was good we did the SHAP analysis too. And while the brain connectivity features didn't show strong correlations earlier, SHAP does reveal that they still contribute, but with mixed and subtle effects, which points to more complex and non-linear relationships that our model is capturing, which we found good. Next slide, please. Following the ADHD SHAP analysis, we also looked at what influenced the predictions in sex. Here we can see that the model relied heavily on behavioral patterns that distinguish boys and girls, which is important since those same patterns influence how ADHD presents. This supports our two-stage approach since we gave ADHD model a stronger foundations to interpret behavior in context by giving the probabilities for the sex. Next slide, please. These PCA plots show that neither ADHD nor sex is linearly separable in this reduced space. PCA didn't give us these clean clusters, but it did help us compress these nearly 20,000 features into a more manageable form. Next slide, please. Next slide. Now moving on to the model, like previously mentioned, we followed the two-stage classification approach. In stage 1, we predicted sex using a voting ensemble of XGBoost, IGBM, and logistic regression. Then in stage 2, we used that probability as an extra input, so sort of feature engineering to predict ADHD. The idea was to let the model adjust how it interprets behavioral traits depending on the likelihood of the sex of the participant, which reflects how ADHD presents differently in girls versus boys. We trained this whole pipeline using 5-fold stratified cross-validation, keeping the balance of both ADHD and sex in each fold, and then we used out-of-fold predictions to fine-tune our thresholds. Next slide, please. Building on that, we aligned our thresholding strategy with the competition focus on weighted F1 score. So like our previous presenter said, we gave more importance to cases where both ADHD and female sex were present. Next slide, please. Next slide. By the end of our analysis, what stood out to us was that behavioral and brain-based patterns aligned and diverged across sex and ADHD. From these images, from these connectome visualizations, we can see that differences in brain connectivity do exist, especially in the frontal and parietal regions. They're far more subtle than behavioral distinctions. This complexity may be why the models trained only on neuroimaging struggled without the clinical context. Interesting, both sex and ADHD, the brain doesn't really present clean, isolated patterns, but they do add this complementary value to our model when we combine the connectome data with the behavioral and demographic features. Next slide, please. And one of the most important data checks we did was to see if the feature distributions were consistent between training and test sets. We used the Kolmogorov-Smirnov test. We found that some variables like enrollment year, study site, and scan location had big significant distribution shifts. From a clinical perspective and a logical perspective too, a diagnosis shouldn't really depend on where or when someone got scanned. So if those features carry too much weight, we might end up with a model that performed well on paper, but doesn't really generalize, or worse, picks up on technical shortcuts instead of real medical patterns. That is why this test was so important for us. It helped us separate what the model was learning from the actual clinical signals versus what might just be noise from how the study was designed. Next slide, please. In the end, our model worked because it mirrored clinical reasoning. We used sex as a meaningful input, combining predictions into stages, and we relied on a well-calibrated ensemble. What didn't work were strategies that added complexity without benefit, so like over-segmenting the labels, forcing balance with SMOTI, or removing connectome features just based on statistical shifts. This balance of clinical logic and model simplicity turned out to be the key for us. With that in mind, I'll wrap up quickly by recapping what made our approach effective and why we think it held well across datasets. Next slide, please. Our model's strength came from using meaningful behavioral data combined with the brain data, combined with brain data. We also used a simple but effective voting classifier ensemble to predict sex, balancing the power of tree models with the stability of logistic regression. We aimed for models that generalized well, and seeing that consistency confirmed that we were on the right track. I think something that we noticed was that even our simple reach regression had a good performance, which showed that the signal in the data was clear enough to be picked up by even a linear model. So really that really helped us, even with a simple model, to know that we were on a good track and our model was showing generalization. And that is why we picked this model for the final private test data set. Thank you for your attention. We'd love to hear your questions, and I'm sure my teammates would be happy to answer any additional questions in the chat too. Thank you.
Wonderful. Thank you so much. Wonderful presentation and congratulations.
So
Thank you.
first, that was fantastic. I just not really a question, but it's a comment about the color vision. So it's actually documented that there is a higher rate of color blindness in males, and that females also have better color distinction. So anyway, that's interesting that you found that, but it's definitely something that's been observed before in clinical kind of measurements. Yep.
Yeah, that is definitely interesting. Now that I think about it, most colorblind people I know are men, so
Yeah.
it checks out.
And yeah, and it's interesting because that it's like the pathology is more in males, but then even non-pathological people who can see all the colors of the spectrum, females do better at discriminating colors that are closer together. Yeah. And there's this so-called like super detectors for color, and they're mostly female. Yep. Anyway.
I also wanted to congratulate you, and I think that you highlighted some of the, winning approaches that you use, like a clinical approach, thinking of what makes sense, the logic. But I also wanted to congratulate the way you visualize the data. I think that it was great to see data in plots and the way you really like thoroughly went through and looked at the data. And I wonder whether you have any comments about how that helped with this challenge.
Yeah, clearly, for us, EDA, exploratory data visualization, was really important. We always spend a long time just looking at the data, understanding the data. We knew from last year that whenever we have this was a new problem for us. We're statistics students, where we deal with economic problems all the time. The medical field is very foreign to us. So we knew that pre-processing is an important step, especially when dealing with medical data. That is why, if you look at our data imputation methods, they weren't that complex. They weren't as complex as we would have done, for example, for an economic case. That is because we looked at the literature. We saw that when dealing with medical data, it's really important to not use very advanced methods to impute, because you might actually put a value there that is wrong. Outliers are really important in medical data. I mean, in school, I was taught you need to remove all outliers, right? But here in medical data, it's actually important to analyze those outliers. So that was definitely something that we looked into. We wanted to study a little bit about the topic, about how to deal with medical data. What does that mean? And it was definitely different. Pre-processing is very different when dealing with medical data versus economic data. So yeah, but we enjoyed it. It was such a challenge, and we also enjoyed just looking into our own brain as women. It was very interesting to see the different behavioral types between men and women, and also we think it's an amazing problem. I mean, sure, we discovered that behavioral traits, like in clinical psychology, help diagnose ADHD. But I think what was interesting from our perspective, from the data science perspective, was that we also used the brain connectivity data to sort of bring more insight and perhaps help clinical psychologists. I don't know, perhaps you could give us more information into how our findings can actually help clinical psychologists diagnose ADHD cases.
Yeah, thank you. Fantastic. Thank you so much.
Thank you.
Yeah. Thank you. Well done. All right, we will move on to the next team. Next, we have the top student team, which is Team KLE Data Stormers from Habalai, India. And Aisha Manyar will present on behalf of the team. So go ahead, Aisha.
Thank you, Valerie. I hope everyone can hear me.
Yes.
Yeah. Hi, everyone. I'm Aisha Manyar from the top student team from KLE Technological University, Hubli, India. We are thrilled and proud to share that our team is recognized as a top student team globally and secured 6th place on the leaderboard. I would like to thank the WiDS Datathon team for hosting such an exciting and impactful global competition. It was not only a lot of fun, yeah, but also an incredible learning journey for us. Next slide, please. It's an honor to represent my team, the KLA Data Stormers. Joining me are my amazing teammates, Gauri Banapurmat, Michelle Hulgeri, and Tanuja Ratan. Together, we are pursuing BE in computer science with specialization in artificial intelligence at KLA Technological University. And today, I am here to walk you through our approach and insights. Next slide, please. Yeah, just a second. So, background. Yeah. This was our team's first venture into one of the most prestigious and widely recognized global data science competitions. And honestly, we were both nervous and excited to take on the challenge. Thanks to our School of Computer Science and Engineering for introducing us to this opportunity as a part of our exploratory data analysis coursework, which gave us a strong foundation in Python, linear algebra, statistics, and EDA, helping us to understand the data, spot patterns, and apply the right modeling techniques. It felt amazing to apply classroom learnings to such a real world global challenge. Yeah, next slide. To give you an idea of the features we used for ADHD prediction, the most impactful features actually came from both metadata and fMRI data. Key metadata features included SDQ hyperactivity and SDQ externalizing. And from fMRI, we selected around 18 top columns based on their correlation and importance scores. And for sex prediction, the top 20 features were mostly from the fMRI data. Dimensionality reduction played a key role here as the raw data was highly dimensional. And yeah, we choose XGBoost for ADHD because it's robust and handles tabular data well. And for sex prediction, we went with light GBM, which is faster and more efficient, especially important when we are working with large data sets. Yeah, next slide, please. And yeah, we did all of this on Google Colab, which honestly became our best friend. It gave us free access to GPUs and great processing power for handling large data sets. And our key libraries included pandas and numpy for data manipulation, scikit-learn for preprocessing and model building, matplotlib and seaborn for visualization, joblib for model persistence. For ADHD prediction, training took approximately around 25 to 30 minutes on GPU, whereas for sex prediction, it took around 8 to 12 minutes thanks to its speed and efficiency. Next slide. Now, coming to one of the most important stages, feature engineering. This is where we really shaped our input data to make it work for our models. For ADHD, we started with correlation analysis to identify relationships, followed by manual feature selection. But for the sex prediction, things were actually more complex. So we applied PCA, a dimensionality reduction technique, to focus on the most informative brain activity signals while keeping the model lightweight. Next slide, please. Yeah, now that we had our features ready, the next step was to understand which ones actually mattered the most. So we visualized the top 20 features our models relied on. This plot shows the top 20 features that our model used for predicting ADHD. You can clearly see that SDQ hyperactivity stands out, which makes sense since it is one of the core symptoms of ADHD, right? Next, please. Here is the same plot, but for sex prediction. Most of the important features came from fMRI data. This showed us that brain activity patterns played a significant role in helping the model distinguish between male and female predictions. It was super helpful to actually see what the model was focusing on, which made it easier and trust and tune the things. Next. Yeah, now coming to how these features impacted the predictions. For ADHD, SDQ hyperactivity was a major driver. For sex, SDQ emotional problems combined with fMRI patterns played a strong role. This shows that both psychological behavior and neurological signals influence the prediction outcomes. Next. So yeah, after identifying the key features, we wanted to visualize how they influence the model's decision. And that's exactly what this partial dependence plot shows. So in this plot, we looked at how the hyperactivity score affects ADHD prediction. You can see a clear upward trend as the score increases. The model is more likely to say the person has ADHD. And it totally makes sense because hyperactivity is one of the core symptoms of ADHD, especially in younger ones. Next. And here we checked out how emotional problem scores affect the prediction of gender. As the emotional score increases, the model predicts a higher chance of the person being female. Again supported by real behavioral studies, females often report more emotional or internalizing symptoms, and our model picked that up really well. Next. Next. Let's now dive into how we trained our models. So for ADHD prediction, we initially split the data into 80:20 train is to test ratio. Although the initially accuracy was low, further model optimization and tuning over more epochs improved the performance, achieving an F1 score of 0.8584 with balanced accuracy. But for sex prediction, we experimented with various classification models, including XGBoost as well. But the results were unsatisfactory. Then we thought of applying dimensionality reduction technique called as principle of component analysis, and light GBM came out to give satisfactory F1 score of 0.5957. Next, please. Now coming to whether we used ensemble methods, here is how we handle that for both the tasks. For ADHD, we stuck to one solid XGBoost model. It's already an ensemble. And with proper tuning, it gave us great results. So we didn't find the need to add more layers. But yeah, for this X prediction, we did a bit more. We used light GBM and trained it with 3 different seeds with 5-fold cross validation as mentioned. We then averaged everything to make it more stable and fine-tuned the threshold to get a better F1 score. Next, please. Once the models were built, we stepped back to ask what made our solution so stand out. It wasn't about doing more, it was about doing the right things, a clean pipeline, smart feature selection, task-specific models, and most importantly, the fusion of metadata and fMRI that really gave us a full picture. Next. Now let's get next, please. Now let's get to one of the coolest and most interesting finding from our work. We observed that males aged between 4 to 10 years show higher hyperactivity scores as compared to females. This finding of ours got validated when our college hosted a WiDS workshop. A well-known neurologist from GMC, Saroja AO, explained about the differences in male. Exactly what she described. It felt amazing to see our data reflect real behavioral patterns. That's when we realized that we weren't just predicting the labels, we were actually mapping real human behavior. Next, please. Furthermore, metadata features and fMRI played an important role for both ADHD and sex prediction. This was clearly reflected in the variable importance plot as we showed earlier, with SDQ hyperactivity topping the ADHD list and fMRI features dominating for sex prediction. And honestly, these visualizations really helped us understand what the model was focusing on, making it easier to trust and tune our approach. Screenshot. Next. Surprisingly well, the ADHD model still got an F1 score around 0.81 compared to 0.8584, just a small drop. But for sex, we kept almost 90% of the original performance. This proved that with smart feature selection, we could build models that are faster and scalable without losing much accuracy. Next slide, please. So here's a quick wrap up. Our biggest strength was blending behavioral data with brain data. We used PDPs to get a better feel for how features influence the predictions. And honestly, having a clean, modular, and flexible pipeline made things so much smoother. It really kept us on track and made improving the stuffs very easier. And now, our favorite part of this journey, the late night calls, the debugging models, and celebrating tiny improvements. And of course, the moment our Kaggle rank shot up, we screamed on the call. That thrill was priceless. Next. So that brings us to the end of our presentation. I just want to take a moment to thank the WITS organizers. It's been such an exciting and impactful competition, and we are really grateful for the opportunity to share our work here. Also, a big thanks to everyone attending the panel discussion today. We really appreciate your time. We are truly thankful to our mentors and faculty at Kele Technological University for their continuous support throughout this journey. We are honestly proud to represent our college as one of the top student teams globally. That's it from our side. Thank you so much. And yeah, we would be happy to take any questions.
Thank you. Congratulations. And thank you for, I know your instructors played a part in bringing this to your classroom. So we appreciate all of your hard work.
Yeah, congratulations. That was amazing. Both your ranking, but also the presentation was excellent. So yeah, congratulations.
Thank you so much.
I really enjoyed the explainable side of it when you went back and look at the partial dependency between the inputs and the target variables. Did you do that for other inputs? I remember you did it for hyperactivity, respect to ADHD. Did you try other variables there?
Yeah, but we tried, but we thought that hyperactivity is actually the most impactful feature, like which was affecting the prediction of ADHD, right? So we thought of doing it for like hyperactivity itself.
It sounds great. Yeah, that makes a lot of sense. Thank you.
Great. Any other questions for or commentary for Aisha? All right. Well, wonderful job. Thank you so much. Excellent presentation and congratulations on your top position.
Thank you so much.
You're welcome, Aisha. All right. Next, we have the top student team, Team Overfitting Masters PSUT from Amman, Jordan. And Reem Zagir will present on behalf of the team. So over to you, Reem.
Oh, hello.
Hello. Perfect.
Hi, everyone. I'm Reem, and I'm here to present on behalf of Team Overfitting Masters from Princess Sumaya University for Technology in Jordan. Our team includes Abdullah, Ammar, Sabah, and myself, and we're all second-year students majoring in data science and AI. We're really proud to have placed 7th globally in this year's WiDS Datathon. Today, I'll walk you through our approach and some of the unexpected insights we gained along the way. Next, please, next slide. Next. Okay, since we don't have a ton of experience with neuroimaging, we focused hard on building a clean and disciplined pipeline. Next, please. Next, okay. First, let's start with the SEX-F task. We started by flattening a 200 by 200 fMRI matrix that transformed into 136 features using network-wise and mean aggregation based on the Shafir 200 atlas. And we used We also applied gain and imputation at k equal 5 for missing data and removed leakage features like MRI site, scan year that turned out to be a major turning point in improving our generalization performance. What really surprised us that we used the entire 19,900 dimensional vector without PCA. Our deep model actually performed better, so we leaned into complexity and trusted the model to extract useful insights. Next, please. Okay, for the ADHD, we used ICA on the connectin vector to reduce it into 220 dense components. And when reading through the STQ and APQ, we found out that some of the columns were already aggregated, so making more aggregation on aggregated features didn't really make sense. And here we use again the KNN for missing data, and we removed the features MRI and scan year. Next. Here we did the heat map. We found that hyperactivity is the most effective feature. And as I said before, we saw the STQ and hyperactivity. This is it. Next, please. And this is here why we used ICA. This is a sample of normality plots for ICA features, shows that it's suited for linear model, which confirms our decision to using ICA was a step in the right direction. Next, please. Next. Okay, for the 6F model, we used a 2-stages pipeline, the teacher model and the student model. The teacher model, it's a deep neural network with calibrated outputs. And the student model worked on smaller sequential DNN trained on soft label mean squared error. And we tuned the threshold at 0.19 for best classification. Next. About the ADHD, it really surprised us. We tried many model types, decision tree, GNNs, but none performed as well as logistic regression with L1 regularization. It turned out the ICA features made the problem highly linear, and regularization helped the model converge to small, stable set of useful features. So despite experimenting with deeper and more complex architecture, a simple and cleaner one. And we use a threshold at 0.65 to fix bias towards ones. Next. And here's, as we said before, the hyperactivity feature was the most effective. Next. Okay, important findings about 6F. Due to the nature of the model needed for predicting the 6F, ANs and GNNs, known as black box models, our feature selection was based on our own research and intuition. And soft label distillation helped smooth training signals and stabilized predictions. And as I said, removing site-specific features like scan year, site location, reduced leakage, and really improved generalization. And in the 6F, we had a problem that female detection in test set was difficult due to class imbalance and feature distribution shifts between the test and train. Next. Okay, weirdly enough, categorical and quantitative features alone achieved fairly good accuracy at 0.74. PCA, when we tried PCA on ADHD, it worked to some extent, but logistic regression with regularization seemed to always converge to a small list of features, so ICA emerged as an option. As I said, we tried decision tree and GNNs, gradient boosting. They all failed to achieve a notable accuracy. The data is built for something linear because it's normally distributed. Next. And yeah, that's it. Thank you. Is there any questions? I'm happy to answer, and my teams as well.
Congratulations. Wonderful job. Yeah,
Thank you.
Congrats. Yeah, it's fun to see neural networks working on the same problem. It's kind of different from what we've seen so far. Can you give some more details on the teacher network architecture and the student architecture? How many layers did you have? What did you use for hyperparameter optimization? Weren't you scared of overfitting? How did you think about it?
Well, you can
actually,
see.
can I answer that? Because I specifically
Yeah,
trained the
Abdullah,
model.
he's
It
the one
was my
that worked
idea.
on it really.
It was my idea. I actually imposed it on the team. They were like, no, they weren't very familiar with the method. I actually discovered it while researching for the competition. So basically, we just noticed that too many hard labels resulted in, let's say, tight thresholds. So when training a normal neural network, at some threshold, there would be a great difference between the ones predicted and the zeros predicted. So that was just not working for us. It didn't give us good results. So after some discussions with our doctors and some research, we reached to the distillation and teacher-student model approach, where it basically just tries to soften the models. It had some costs because we risked accuracy. The labels weren't as accurate as they provided in the data test, but it gave us the advantage of trying to predict probability more than a hard label. The problem with overfitting is, the teacher model is overfit actually, but the student model, we actually try to maximize the mean squared error after training. So we came to the conclusion that much more error in the training dataset meant less error in the test dataset. I don't really know why, but it's probably due to the lack of overlapping in the features. We actually just used 4 layers. It was fairly simple. Started with the whole 20,000 feature column, scaled down to 1,512, then 164. Then we're going to the last input, the last output layer, which was simply a one.
It's great. Thank you for the details.
Yes.
Thank you, Abdallah, for that explanation.
Yeah, you're welcome, and thank you all for this for the organizing of this competition. It was actually a fun ride, and being our first time, we actually felt so lost, but your help was actually appreciated. Big thanks to all the participants, other participants, and congratulations to all the other winners. And thank you. Yeah.
Wonderful, thank you. All right, well, with that, we'll move on to the next team. Congratulations once again. Okay, next up, we have the top high school team. This is high schooler Isha Vanamala from New Jersey here in the United States. It's an honor to hear from you, Isha. So over to you.
Well, hi everyone. I just want to say thank you to the WiDS team and the Kaggle team first for doing this amazing datathon. I definitely learned a lot about the way, and it was a really fun experience. So thank you again. And let's go on to background. So next slide, please. So yeah, I am currently a high schooler, so I don't have too much professional experience, but I think that some things that helped me approach like the datathon in the first place was that I'm currently taking AP Computer Science Principles, and I've definitely made other machine learning models before, so that helped me like learn about like what to do at different stages across the journey. Next slide, please. Okay, and now for a summary of the project in general. This project used a two-stage logistic regression approach. So first, a model was trained to predict sex, and that predicted probability was then incorporated as an input feature for a second model to predict ADHD outcomes. And to ensure an unbiased evaluation, the pipeline employed repeated stratified k-fold cross-validation with 5 folds and 5 repeats. This method repeatedly splits the data into 5 subsets, maintaining the same class proportions in each fold as in the overall data set. Each subset then took a turn as a validation set, while the others were used for training. The prediction thresholds for each model were optimized based on the F1 score to achieve like a trade-off between precision and recall. And feature importance analysis revealed that for the sex prediction model, color vision CV score and SDQ emotional problems were the most influential variables. But for the ADHD model, interaction terms were the most important, showing the value of combining like these effects between variables. For tools that I used for this project, I used scikit-learn for modeling and evaluation, pandas for data manipulation, matplotlib and seaborn for visualizations, and iterative imputer with lasso for missing value imputations. It was around 15 seconds to train this model, which was pretty efficient. Next slide, please. Now on to feature selection and engineering. Next slide, please. Okay, so for the important feature transformations, the first one definitely be imputation. Missing values in the dataset were filled using iterative imputer, which estimates missing entries based on other features in the data. And I also used standard scalar for standardization. Features were then standardized using standard scaler, ensuring that all variables had a mean of 0 and a standard deviation of 1. Interaction terms are also created. For example, for the ADHD model, new features were created by multiplying the predicted probability of being female with other variables, capturing combined effects. In addition, basic interaction terms were generated by multiplying pairs of original features, which allowed the model to learn relationships between variables. I also used feature set selection, which were stored in the variables feature sex and feature ADHD. This included features like STQ, STQ, difficulties total. Next slide, please. Okay, and now on to my variable importance plot. These are the two variable importance plots, and it shows that the most important feature for the sex model had a positive correlation, while the strongest feature for the ADHD model had a negative correlation. I think color vision CV score was the top model for the sex model because the Ishihara color test measures red-green color deficiencies, which are more common in males compared to females due to it being X-linked recessive. For participants with low scores on this, the model was assigning almost all of them with a sex F score of 0. Next slide, please. Over here is my partial plot for the top feature for the ADHD prediction model. This was the probability of the patient being female with the Alabama Parenting Questionnaire Parent Report positive parenting score. As this feature increases, the partial dependence of the outcome decreases, suggesting a negative association. Next slide, please. And over here is the partial plot for the most important feature for the sex prediction model, color vision CV score. And originally the test is from like 0 to 14 plates, but it was standardized, which caused these new values. As this feature increases, the partial dependence increases, suggesting a positive association. And I use logistic regression as my model, so when plotting both these features in log odds, it became linear as expected. Next slide, please. And now on to training methods. So I use logistic regression with L1 regularization and cross-validation for both prediction tasks. The data was first standardized using standard scaler, and then missing values were imputed using iterative imputer to evaluate the model performance and ensure the generalizability. Repeated stratified k-fold was applied. The data was split into 5 equal-sized folds, ensuring that the proportion of classes in each fold was approximately the same as the original data set, helping in handling class imbalance if it was present. And in each iteration of the cross-validation loop, 1 fold was used as the validation set, and the model was trained on the remaining 4 folds. This process was repeated 5 times, with each fold serving as the validation set exactly once. Thus, the model was trained and evaluated on different subsets of the data. This helped in obtaining a more robust estimate of the model's performance and ensures that the model generalizes well to unseen data. Thresholds for the classification were selected by optimizing the F1 score, trying to balance precision and recall for the best predictive accuracy. Next slide, please. Now to important, interesting findings. Using interaction terms between features and using sex probability to help predict ADHD status really helped improve model performance. And as you saw on like the partial dependence plots, these interaction terms were some of the best predictors for ADHD. Next slide, please. So one interesting visualization that I found when exploring the data was this correlation heat map. The solid red diagonals because each variable was on both the x and y axes, so the correlation was exactly 1, and the negative correlation values indicate an inverse relationship, while the positive correlation values indicate a positive relationship. This particular heat map could help find relationships between features and potentially redundant ones. Next slide, please. And now on to the simple model. So the subset of features that would get me 90 to 95% of the final performance were the top 5 features for the sex model: color vision CV score, STQ, STQ emotional problems, STQ, STQ prosocial, like the STQ, STQ hyperactivity, and MRI track AJ scan, which was particularly interesting. And it suggests that maybe males and females received like their scans at different ages, suggesting that like females might be like getting their scans later than boys who express hyperactivity, or some type of cohort effect. And for the ADHD model, it was just like the top, for both of them, it was just the top 5 features from the original model, and this scored around a 0.76 private score. Next slide, please. So now on to the solution overview. The interaction terms are some of the strongest predictors of ADHD, which mimics clinical differences between presentations of ADHD. And one thing I really liked across the Datathon was just discovering these meaningful relationships and learning more about like the data through data dictionary that the dataset provided. And next slide, please. Now on to question and answer. Yeah, that's really it. Thank you so much again.
Great job, Isha. Wonderful presentation. All right, any questions or comments for Isha?
Really love the presentation and the work. Thank you so much. And I agree that the interaction terms that you found are very interesting. I was also interested in the iterative imputer you use for the missing data. Did it make a notable difference compared to imputing with the median or the mode? Why did you just choose it?
So originally, I remember, I think I used median originally. I don't think there was a big difference in using iterative imputer, but I just definitely liked how iterative imputer is a lot more generalizable in that like it uses the other features, and I liked that. I was also like learning across the Datathon, so I learned about iterative imputer, and I was like, okay, I want to use this. I want to learn more about this tool, and I think it did give me like a slight advantage over median. So I decided that I wanted to stick with it and like continue adding different like training things on top of it.
Yeah, and maybe it did build on the interaction between the features to impute better values. So it kind of all makes sense. Thank you.
Amazing. It's so impressive to see this work done early on. And so, you know, we're very impressed by your insights. All right, wonderful job. Shall I move to the next team? Thank you so much, Isha. Congratulations once again for your performance. All right, last but not least, we have the top WiDS Datathon first timer, Quinn Nguyen from Hanoi, Vietnam. So over to you, Quinn.
Hello, everyone. I hope you hear me well.
Yes.
Yeah, I'm Queen from Vietnam, and I'm a first timer and also a solo player to this competition. And I'm so excited to share with you my humble approach to the problem this year. Yeah, so firstly, a bit about myself. Could you go to next slide? Yeah, next slide, please. So I'm now working in a AI company as strategic operations, where I use internal data for decision making and like promote change across the organizations. But through my career, I have been defining myself as kind of non-tech person because of my background at the university and my different roles through my career. But I'm always attracted by technology, innovation, and I love to play with data. So now I'm officially following my master degree in information science and machine learning. Yeah, so in short, I think I'm kind of a lifelong learner who growing myself as a woman in technology and more specifically a woman in data science. Yeah, so that's pretty much about myself, and let's go to the approach to the problem. Yeah. So this is the summary of my approach. As the problem statement, so we need to predict the ADHD and sex of the individual. So I separate into two different like problems and like predict separately. Although the approach are quite the same, so we train the different as like models as the estimators, and finally feed into the final voting classifier and have the prediction. But the difference are in the firstly in the data feed into the models. I will explain in the next part. Yeah, and the details of the selection of the models for its prediction, and also the threshold choosing for the prediction. Yeah. So let's go to the more details of my approach. Firstly, from the feature engineering. So very simple for the missing value imputation. So for the quantitative data, I impute by mean, and for categorical data, impute by mode. Yeah, and after that, we go to the scaling the data. Could you go to the next slide? Yeah, so for the categorical and quantitative features, we use the standard scale for most of the features. Only one skew detected feature as the color vision here is kind of quite skewed. So I use the power transformer for scaling. And the functional connector matrices are kind of like special because I think like the nature of the data are different. So I find different approach like searching in the internet and find the best practice when dealing with kind of like brain data. And I found one library like named Neuro-Harmonized Library. So it helps to harmonize the data with the assumption that the brain data collected from different sites, from different like scanning device, I assume, will have the different results. So it has to harmonize the brain data across the location. And as one insight, I found that like in the test set of the data, like it does not include all of the locations as in the training set. So finally, I found that like this library have a lot on improving the result. Yeah, so please go to the next slide. And this about the feature importance and feature selection for ADHD prediction. So here is the assumption on the most important features: hyperactivity and externalizing. And we do not see like the brain, like the MRI data features in the most important features. And after like experiments, so I exclude all the functional connection matrix data for the ADHD prediction and only use the categorical and quantitative data. Yeah, and for the sex prediction, could you go to the next slide? Yeah, so the most important features here are all from the brain data. So I include firstly include all the quantitative and categorical features and select like 100 most important features from the functional connector matrices as the features for training the models. And in short, could you go to the next slide? So yeah, ADHD prediction, we use full set from categorical and quantitative data. And for sex prediction, we use like all from categorical data, quantitative data, and 100 features selection from the functional connection matrices. Yeah, so then, yeah, just go to the training part. As I also summarized in the first part, so it's also simple. We like train the models, different like experiments on a lot of models, and then like select like some of them as the estimators for the final voting classifier. And besides the F1 score, I also like generate different other metrics as the reference. And the F1 score here also the same as some like teams presented before. So I also use the weighted F1 score because it's stated in the problem at the beginning. So I think it has higher chance to get like higher result. Yeah, so to double for the ADHD and female outcome. Yeah, so final voting and the threshold for final prediction for ADHD is 0.5. Yeah, and for the next model for the sex prediction. So could you go to the next slide? So it uses the other set of estimators. And in the end, we like go through the threshold selection, and the threshold like 0.3 is the best one to have the best result. So yeah, the set of the estimators here and the threshold 0.3 is the best one we choose for sex prediction. And finally, combining them to have the final result. Okay, could you go to the next part. I think it's the simple model, right? The next slide, please. Yes, the simple model, I didn't do it in the competition, but this one part I need to look back after the competition and like to share the results. So I think there's no single model alone could like represent the final outcome, because I believe each model can contribute different perspective to improve the overall results. But I found it helpful to select the features again. So after like having the final models, I do the feature selection again, and we have the top here is just the visualization, but this is like the top 10 of ADHD and top 10 for sex prediction. I think for ADHD is like does not change much because the hyperactivity and externalizing still the same. The top 10 of like sex prediction change a bit, but I think not much. Yeah. And finally, for the final simple model, I could go to the next slide. So my final selection for the simple model, so ADHD prediction still utilize a full set of the quantitative and category data, while in the sex prediction, I chose only like 50 most important features, including both the quantitative, categorical, and the brain data. And as I just like review, so the 50 features here mostly come from the MRI data, and it includes also the hyperactivity and the emotional problem feature from the quantitative and category data. And as a result, I think the simple version is not like it even perform better. It quite surprising a result. The validation score is like slightly lower. The public score are like slightly lower, and the private score significantly higher. So that's quite surprising. I wish I just did it before in the competition. Yeah, but it's a good lesson that like after training the models, and we can look back and find like select again the most important and train again, and yeah, have the better result. Okay, so that's pretty much about my approach, my findings and lessons from the competition. The first point is about the power of ensembling in this problem is quite like big. So I think if I do not use ensembling methods, so I cannot get that result. The second point is about feature overload. So I didn't use the functional cognitive matrices data for ADHD. It's not only about the processing time or like computing power, but like I try using that data for ADHD prediction, and the result was worse. So I just like ignored in the ADHD prediction and just used for the sex prediction. Yeah, and the final insight is from like the neuroharmonize, which is something new. I just explored when solving this problem, and it shows some kind of like good impact to the solution. And also the combination of different estimators in the final voting classifier also like kind of surprising good result. And yeah, it showed the power of experiments. Yeah, so the next slide. These my lessons, also the insights from the competition. So I learned from the power of ensemble models, the power of experiments, and being persistent on the way. And I also learned how to utilize the power of community, because I went through some kind of discussion on the competition, and I got a lot of insights, and I got kind of inputs from my experiments to improve my solution. And also luck, I think I'm the luckiest first timer here to receive this big encouragement from the organizer. Yeah. And like above all, could you go to the next slide? So I think this the most important step I took this time is to just to start because I'm the first timer. And yeah, I think this is the most important. I just start and I learn a lot, and I like have lucky and I also have motivation to continue my journey in data science and have motivation to continue in the next year competition. If you still continue this datathon next year, so I will try again. Yeah, so thank you for organizing such a wonderful event, and yeah, I'm welcome for Q&A.
Thank you, Quinn. You said it perfectly. I think just starting is always the first step. And so we like to make these competitions approachable for anyone to feel like they can use it as a launch pad for their data science journey. So what a great note to end on. Questions or comments for Quinn?
Well, congratulations. I really liked your conclusions. I think they're very elegant and they summarize really other findings that we have for this competition. And I really appreciate also the use of the fact that you try to harmonize fMRI data across different sites. I think that's a great step, and that is also very important. I have a question for you regarding that, which is, well, first of all, how you found out that that was an important step, and also how much did that improve your model results?
So you're mentioning about the neural harmonize?
Right. Yeah, correct.
Yeah, so at first I was quite like confused with that data because it has a lot of data and like kind of new and with a lot of like expertise, I think. I think someone with the insights from like the brain, so we will like know more about it. So I try to search in the internet first to find the best practice, like how we can handle kind of brain data. And I found some solutions and I tried. And I think it's simple enough for kind of beginner for me. So it's easy for implement. And before that, I didn't use that to harmonize my that library, and the result is like slightly lower. I didn't remember like correctly, but like I confirmed that like it improved the final result, and I just like go with it until like the last models that I use.
Thank you. Yeah, congratulations.
Thank you.
Great. Any other questions for Quinn? All right. I see a comment in the chat. What a lesson in data visualization and data storytelling. So yes, great job, Quinn. Well, thank you so much. Congratulations on all of your hard work. Thank you. All right. Well, that concludes today's WiDS Datathon winners panel discussion. I want to say it's really impressive to hear all of your different approaches to the problem. There's no one way to do it. And so I think a big learning here is just there's so many different ways to tackle the Datathon challenge. And so we're impressed by all of your findings. I want to give an opportunity. Do you guys have some last comments to say to everyone on the call? Ariana, Nina, Amy.
Yeah, thank you so much for presenting your results. I was impressed by the methods you used and the little tricks and smart ideas here and there. But today, in addition to that, I was impressed by how you presented them. So yeah, super inspiring. Keep it going. We hope to see you next year.
Yeah, thank you so much for participating in this. It was kind of the Bowers Bowers WBHI first time partnering with WiDS and Kaggle. So I'm excited to see all the enthusiasm from everybody. Yeah, thank you so much.
Yeah, and thank you so much also for bringing up some of the most interesting things I've heard about the data set itself. As data providers, we always love to see how people explore the data, visualize the data. So I learned a lot from our own data as well through you and through your work. So thanks for participating, and I really enjoyed this.
Yeah, thank you, everyone. Thank you for your sharing your solutions with us, and also congratulations to everyone else who participated in the challenge. This call is being recorded, so we will share this on the WiDS YouTube channel within a week or so and send it out. And we'll also share out the slides of everyone's findings. And then additionally, all the winners have their results posted on the Kaggle discussion board. So if you want to dig in more into a certain winner's solution, you can go to Kaggle to find that. All right. Well, take care, everyone. I hope you have a great rest of your day. And thank you so much for joining us.
Thank you.
Thank you.
Goodbye.